Hello, welcome to Unit 11 in Algebra 2. Unit 11 is about rational expressions, equations, and functions. So our first lesson, we're going to look at simplifying some basic rational expressions. So basically, you can think of this unit as being a more thorough investigation of the mathematics of fractions. We've been dealing with fractions a little bit all year, but now we're really going to look in depth at some expressions. Let's start by simplifying some expressions. Let's start with 16 over 56. The way I would simplify this is I would think of a common divisor to 16 and 56. And hopefully you realize that that would be an 8. That's the greatest common divisor. So if I divide 16 by 8, I would get 2. And if I divide 56 by 8, I get 7. So pretty simple there. Let's take a look at one a little bit more complicated. This is similar to some of the work that we did in the last unit, when we talked about exponents. 4 and 6 are each divisible by 2, so I can reduce that to 2/3. X cubed and x can be reduced to an x squared. And y to the 6th over y to the 8th can be reduced to y to the 2nd. Now let's take a look at this one. 6 plus 10 over 6 plus 2. So question, can I just reduce the 6's out and say that that's 11 over 3 if the 6 is reduced to a 1? Or maybe you think they reduce to a 0 and it becomes 10 over 2, which is 5. Well, a little bit of thought will clearly show that that's not the case. We cannot just cancel things willy-nilly like this when there's plus signs. We should instead add these numbers together and get 16 over 8, and then we can reduce that to 2. But I'd like to show you another alternative. We could also factor out something from this. We could factor out, well, of the numerator, I could factor out a 2, and I'd be left with 3 plus 5. And on the bottom, I could factor out a 2, and I'd be left with 3 plus 1. And I could maybe reduce that way. So that's another way to think about it. But again, I'd still have to add it. So we can reduce when we can cancel when we have things factored out. This, if I was to go forward, would give me 8 over 4, which is still 2. So that is possible. What is not possible is just canceling the 6's right away. That's not allowed. They have to be something like this. They have to be factored out in order to do that. But of course, that's probably more work than you would ever want to do. You would just add the 6 and 10 and the 6 and 2 together. All right, let's take a look at another one. 2x plus 8 over x plus 4. Again, because there's plus signs, I can't start like reducing the 8 and 4. We just looked at how that doesn't work. I certainly can't just reduce the x's. Also, that doesn't work. But I can factor something out. I'll factor a 2 out of the top, giving me x plus 4. And on the bottom, I have x plus 4. And remember, the entire denominator is a grouping symbol. And so that also reduces to simply a 2. All right, let's go on. Simplify the following expressions. For simplicity, assume again the denominators are never 0. We're just doing that for simplicity to make sure that we don't have to worry about a divide by 0 error. It makes the math a little easier. All right, so pause the video and give it a try. All right, so you should have divided the top and bottom here by 7, giving you 4/3. On the next problem, we can divide the top and bottom by 3, giving me a 4 on top. Then this is a to the 4th over b to the 4th. All right, on the next one here, please don't just cancel the 4x's. You have to factor first, making this 2x plus 1. And I can factor a 4 out of the bottom, making this x plus 2. And then I can reduce this and this to make it 2. So 2x plus 1 over 2 times x plus 2. Another way you could have thought about doing this is that it is okay to reduce when there's plus if you can divide each term in the rational expression. Since I can divide each one of these numbers by 2, I could have called this 2x plus 1 over 2x plus 4, which is exactly what I get if I distribute that back. All right, let's take a look at the next one. Leave the x minus 3 alone, and on the bottom, factor out a 5. Then this reduces to 1/5. All right, let's take a look at some more examples. Simplify the following expressions. Again, we're going to continue assuming that the denominator is not 0, so I don't have to account for a possibility of dividing by 0. All right, so remember, you can't just cancel out the x squareds. We need to factor first. So I'm going to factor this as x plus 8 and x plus 1. The denominator factors as a difference of two squares, x minus 1 and x plus 1. And then I can reduce the x plus 1's, giving me x plus 8 over x minus 1. All right, let's try this one. 2x squared minus 3x minus 2 over x squared minus 3x plus 2. I'll factor the numerator. And I think I'll make that a minus 2 and a plus 1. That would give me a negative 4x plus 1x is a negative 3x. Then in the denominator, I have x minus 2 and x minus 1. Once again, I'm able to cancel out a couple of factors. Remember, we can only cancel after we've factored it out. So I have 2x plus 1 over x minus 1. All right, let's try the next one. The numerator, I can factor out a 2. And maybe even go further. And the denominator, I can also factor out a 2. Now, those reduce out, and I can factor this polynomial as x minus 7, x plus 2. And the denominator is a difference of two squares, x minus 2, x plus 2. And those reduce out to x minus 7 over x minus 2. Let's take a look at D. In the numerator here, I can factor out a 3x, which would give me x squared minus 3x minus 10. In the denominator, I can factor out, I'll go ahead and pull out a negative 6x, giving me a positive x squared minus x minus 6. Here, the x's can reduce, and this can reduce to a negative 1/2. So the negative is in the bottom, but you can pull it out in front, or I'll even put it on top. I prefer to have my negatives on top. That's just the way I am. And I actually don't need the 1 there, so I won't put it. The numerator will factor as x minus 5, x plus 2. The denominator will factor as x minus 3, x plus 2. So the x plus 2's reduce out, and we're left with a negative times x minus 5 over x minus 3. All right, let's try letter E. The numerator factors as 2 minus x, 2 plus x. And the denominator will factor as x minus 5, x plus 2. No, that's not right. Sorry, it should be an x plus 5, shouldn't it? X plus 5, then x minus 2. Oh, well, we have an interesting situation here. These are almost perfect, but this is a negative x, and this is a positive x. This is a positive 2 and a negative 2. So, in fact, if I factored out a negative 1 out of this top expression, this would become x minus 2. So these two factors are opposite factors, and they reduce to a negative 1. So they do reduce out, but they don't make 1, they make negative 1. So I have negative times 2 plus x over x plus 5. All right, it's time for you to try. So pause the video and try practice 1.2 A, B, C, and we'll stop there and go over them. All right, time to test what you did. The numerator is going to factor to 3x minus 2 and 3x plus 2. The denominator is a perfect square trinomial. It is 3x plus 2 times 3x plus 2. So I can cancel one of those, giving me 3x minus 2 over 3x plus 2. And then there's nothing else I can do. All right, the denominator here, I can reduce the 4 and the 10 by 2, making this 2 and 5. I can reduce the x's, so it becomes 2x to the 4th over 5y, and the 3 from the 9 makes it 6. Notice that I can just start canceling on b because there's no plus or minus sign. That's basically in a factored form already. So when you have pluses and minuses like we did in A, you got to factor it so you can cancel out total entire factors. In B, since they're all multiplied already, they actually already all are factored. Let's take a look at letter C. This is x plus 8 and x minus 5. And in the denominator, I have x minus 5, x minus 1. The x minus 5's cancel, and I have x plus 8 over x minus 1. All right, let's take a look at our next example. We're going to simplify the following expressions. Again, we'll assume the denominator is never 0. Okay, we have a difference of 2 cubes here. Do you remember the pattern? The pattern is a cubed minus b cubed equals a minus b times a squared plus ab plus b squared. And the sum of 2 cubes is the same thing, except for that's a plus and that's a minus. So in my numerator, I get x minus 2, the cube root of x, the cube root of 8, and now I use that to fill this in. X, square that, multiply these two together and change the sign, and square that. All right, in the denominator, I'm going to factor by grouping. I'll group this together, and remember we need a plus, a negative, and group that. So I'll factor out an x squared out of the bottom group, give me x plus 1. And I have to pull out a negative, because there's a negative there. I'll pull out a negative 4, giving me x plus 1. So this becomes x minus 2 times x squared plus 2x plus 4 over, if I factor out an x plus 1, I then have x squared minus 4. Okay, we'll leave the top alone. X minus 2 times x squared plus 2x plus 4. And I'll finish factoring the bottom as a difference of 2 squares, x minus 2, x plus 2. Finally, we get something to reduce out, and our simplified form is x squared plus 2x plus 4 over x plus 1 times x plus 2. All right, let's take a look at letter B. All right, the numerator cannot factor. There's nothing that multiplies to 9 and adds to 3, so I have to just leave that alone. But the denominator is a sum of 2 cubes, so it's x plus 3. The cube root of 27 is 3. Then I square the x, multiply these two together and change the sign, and then square the 3, which happens to be perfect. And remember, there's a grouping symbol all the way around the numerator, so this just becomes 1 over x plus 3. All right, we got, I think, one more set of practice problems, 2 of them. Pause the video and give it a try. Okay, on this one here, we should have used some grouping, I think. We get to factor out an x squared, and we get x minus 3. We get to factor out a plus 2, and we get x minus 3. Then in the denominator, we get 3 minus x and 3 plus x. So when I factor out x minus 3 from the top group, factoring those out, right, I get x minus 3 times x squared plus 2 over 3 minus x, 3 plus x. Now, did you remember what these opposite factors reduce to? They reduce to negative 1. So this is negative x squared plus 2 over 3 plus x. All right, on the next one, we have a sum of 2 cubes, so it factors as x plus 1, and then x squared plus, not plus, minus x times 1, then plus 1. The denominator factors as x plus 4 and x plus 1. So we get to lose those parts there, giving me x squared minus x plus 1 over x plus 4. All right, for the exit ticket, I'd like to just talk briefly about what it means to not assume the denominator can never be 0. So this entire lesson, each one of the instructions always said, for simplicity, assume that the denominator cannot be 0. Let's see what happens if we relax that requirement. So consider x squared minus 4 over x squared minus 3x plus 2. For what values is this expression undefined? Well, it's undefined whenever the denominator is 0. So it's undefined if I were to factor the denominator. not x squared minus 2, just x minus 2. So it's undefined at x equals 2 and x equals 1. If I plug in a 1 here, I would get 1 minus 4 is negative 3 on top, but I get 1 minus 3 is negative 3, negative 2 plus 2 is 0. So those are the values I can't have. But what happens when I simplify this? Well, it simplifies to x minus 2x plus 2 over x minus 2, x minus 1, which is just x plus 2 over x minus 1. So which values of x is a simplified expression to find? Only x equals 1. And how can this be? Well, because we canceled out one of the factors that told us that we were dividing by 0. So the problem is we need to restrict it from the domain. So the domain of an expression can never increase in size as a result of simplifying the expression. So we should therefore explicitly state that the domain is limited. So if I was to simplify this and call this x plus 2 over x minus 1 with the added restriction that x does not equal 2, because 2 was excluded originally. Now we can see from the implied domain that x can't equal 1, and the explicit domain that x can't equal 2. Much more on that later. Okay, I will see you in the next lesson.